I guess you can start. The title is there. Isomorphisms for quadratic field scaling limit. Jean-Dominique Deuschel.
Okay, so bonjour Montréal, Berlin's colleague, and I wish I would be there with you. And thank you very much for the invitation and the possibility to present this joint work with Pierre-François Rodriguez, who is now at Imperial College in London. Here's a little overview. So the content is in 5 parts. First, I will introduce the anharmonic interface model, in particular, talk about the so-called randomorph representation and capacity. The next, we go into Poissonian interlacement with a intensity proportional to a parameter u times the capacity. And we'll present the so-called isomorphism, which is a relation between local time plus 1/2 of the gradient field square in law of 5 plus the square root of u square. And then we'll pass to scaling limits. So the above was the discrete setting. We'll go to the continuous. In particular, we show that the Wick product converges to the Wick product of the Gaussian, continuous Gaussian prefields. And as a consequence, we also have a convergence of the corresponding local time, the Brownian interlacement. And if time permits, I'll give a few details on the proof, which is basically based on Brascam-Lee inequality, the extended Brascam-Lee. And finally, give an outlook on open properties. So first, let me present what is the gradient interface model and what we mean by randomorph and capacity. So as you can see here on the picture, it's an interface model, which is, so the basis is in ZD, and the phi of x indicates the height above or below the interface. Now, what is important, it's a gradient model, which means that the interaction basically in the Hamiltonian, the formal Hamiltonian here, depends on the discrete gradient. Now, forget about the red part for a while. This means that you have a continuous symmetry. And in particular, continuous symmetry makes it very challenging for lots of reasons. In particular, we can only deal with a dimension d larger than 3 for the infinite model. We will see that we have to introduce some kind of tilting, which is written in red here, with both tilting is a magnetic field and also a mass. Okay, so this is a definition. So basically, this would be the model we'll be dealing with. Now, what is important for this model is that we have a randomorph representation. Originally, it was due to Helfer and Churchcon, but used also by a lot of other people like Funaki and Spohn, Stefano and Giacomin, and Naddaf and Spencer. So in order to define the randomorph representation, we're going to look at the dynamical model, which is actually a symmetric one. So by x bar, we consider both phi of t, which is the diffusion, and x of t, which is a randomorph. So basically, phi of t lives on R to the ZD, and x of t on ZD. So the dynamic is in 2 parts. The dynamic of the diffusion is with the generator L1, which does not dip, and the dynamic of the randomorph, which depends on phi with L2. So for the dynamic of the diffusion, we just have a very standard Langevin dynamic, which is generated with, I wrote it here in divergence form. In other words, you have here e to the Hamiltonian, the sum over x. Partial x is just the derivative with respect to the coordinate phi of x, and e of minus h partial of x. So in fact, one way of describing it, maybe the most standard way, is to look at the so-called stochastic differential equation, where you see the drift is just the gradient of the Hamiltonian, and then you have independent Brownian motion. So this makes it reversible. This is quite standard. Sometimes this is called the Landau-Ginzburg model. Now, together with the dynamic, we also have a randomorph. And it's actually a randomorph in a random environment. So the generator is given phi, which is the diffusion. We have a jump rate, u double prime, from x to y, which is a symmetric jump rate. Now, what is important, I forgot to mention, u has the following property that is strictly convex, bounded above and below. So in some sense, the randomorph is a so-called conductance model. Now, what makes it a bit complicated that it depends really on phi. Now, it's easy to see that because of the symmetry, if we look now at the rho d phi dx, which is the measure mu d phi, this is the measure associated with just the Gibson measure, and the counting measure for the x, and this is reversible for the process, for the joint process xt and phi of t. So if we look at, we can define the corresponding Dirichlet form on L2O4, which is the following part. So you have one part which deals with the diffusion, which is E1, and one part which is dealing with the random walk, which is E2. Now what you have to notice is that in some sense, the random walk depends on phi, but the diffusion not. So there's no dependent on x here, where there's one here on phi. Now, so this is it. Now we're going to deal with transient dimension. So we're dealing in dimension d larger than 3. And it's easy to see that this situation, the process, when the random walk is transient, therefore the joint process is going to be transient. And now this is the so-called random walk representation, which allows us to compute the covariance between two functionals. So I take two functions f and g, depending on finitely many coordinates. Then the covariance with this of f and g is, look downstairs, maybe the sum over x. You start your diffusion in equilibrium, and then you take just the summation over x of the partial of f, exponential here, which is just like a Feynman-Katz form, and then xt. So in some sense, you can see that this is nothing else but the green function of this generator, L plus v. In some sense, why we call it a random walk representation, because basically, if you take a very special case, I mean, this is general. So f and g could depend both on phi and x. So there's a very special case where you just put for f of x0, just say, depending x bar at location little x0, and this one y. And this would just be the green function of the random walk in the random environment. But in fact, we're going to use this formula in a much more general situation. This was derived first by Handheld and Spencer, and like I mentioned here above, used in several locations, like in the paper of Funaki and Spohn, and also there's a paper of Giacomin, Ola, and Spohn on this, and Naddaf and Spencer. So this is a beautiful representation because it allows you to compute all kinds of important quantities with this random walk representation. So maybe just to make sure you understand what is the role of V here, there's a V here, which comes here in the Feynman-Katz formula, and this will play an important. Now, in order to define the interlacement, we have to define the capacity. So we are now dealing with a transient process, and now we're going to look at the cylinder. So basically, this is just the configuration phi, and this is K, some compact set in ZD. And we would like to come to define the capacity of this cylinder. So notice that there's here a dependence on ZD, and this is on the phi configuration. Now, in order to define the capacity, the best is just to use the abstract definition, which is just the infimum of the Dirichlet form. F is larger than the indicator function, and it goes to 0 when x tends to infinity. Now, it turned out that we can give an explicit expression for that. This is very classical. So basically, the capacity is nothing else but the average of the electrical charge, which is given here below, and the equilibrium charge, which is just L acting on this function H, which is just a probability starting from phi x, that this is just the hitting time that you hit the cylinder. This is very classical, so we can just apply it to this situation. Okay. Now, why all of this business? Why is it relevant? Now we come to the matter. We're going now to define so-called random interlacement. So we consider now a parameter u, which is strictly positive, and we define an intensity measure on the state of trajectories. So P of u, v, is going to be a Poisson point process of trajectory. So if you look at it, you have two coordinates, you have diffusion and the random walk. And this is the intensity. I'll draw a picture later just to explain you how it works. So between u of u is a parameter, so x minus is what happens before you reach at time 0 the cylinder, and in the future. And it's done in such a way, don't worry about this, it's just a technical fact. Replace it just by u if you wish. So we take the summation over x, mu of x, then you have the past, and then you have the equilibrium charge, and then you go to the future. So in particular, if you just deal with what happens at the equilibrium, just at zero, it's just some coefficient here. In fact, it's easy to see that this is exactly U, just U times the capacity. Now, what you have to be aware that the capacity, this really is a cylinder, so you have both coordinates. Now, let me just show you maybe the best is to draw such a picture. So you have you have trajectories, which you just throw at random with a given intensity. And if you focus on a compact set, like the set here, then basically you have the trajectories coming from far away. They hit here with the equilibrium capacity, the equilibrium measure, and then because they're transient, they go to infinity. Now there's an important property which is called the sweeping equality, which is consistent. In other words, if you take a set K, including K prime, and you look at just the marginal, then by the so-called sweeping equality, you would see that it is consistent. So it goes from one to the other. In other words, you look at your trajectory, there are some which will never reach K prime, okay, which arrive to K prime, and just put them together. In other words, this way of constructing it, this intensity measure is consistent. And because it is consistent, then you can really construct your Poissonian field. Now, what is the main result of this business? I will explain this later, the so-called isomorphism theorem. Actually, it's not a real isomorphism. I will come to that later. It's a kind of a Laplace transform business. So you take a parameter U, a function B with bounded support, which should be small. So C divided, there's a constant C divided by L squared. So the Laplace transform tells you following. So basically, L here is the occupation time. So this tells you how much time do you spend at location X by this Poisson cloud, because it's transient, makes sense. So basically so this is for this measure here. Then you add to this an independent square of the field. And then what you find out is that this has the same distribution as just by shifting the field with the parameter. Now, of course, in some sense, this looks pretty much like a Laplace transform, but there's a little problem in this business. Let me just put a color here. The trouble is the V here. So if the V were non-existent here, because you see you have a V here and you have a V here, then this would just mean that you have the isomorphism, which means that because the Laplace transform agree, it just tells you that the law of the local time, the occupation time plus 1/2 phi squared, the same as the phi shifted with U, if you put it in Poissonian way. And in fact, let's have a look at the Gaussian case. So this was previous result, which was been developed by different author. We'll make a review on the literature soon. The special case, which is a Gaussian case. So where the potential here is just a square. Okay, it's just strictly convex. Then the corresponding measure is just a discrete Gaussian free field, where G for Gaussian. It's easy to see that it's a Gaussian field which covariance is just given by the Green function of the transient simple random walk. Now, in this situation, in the random walk representation, the random walk does not depend on phi. Therefore, in some sense, you could just skip the V here. And you have the so-called Poisson interlacement. So basically, the capacity does not depend on it, just the standard capacity of the random walk. This is the standard interlacement. And then what you end up is precisely what I said, is that under this distribution here, then the sum of the occupation plus 1/2 square is the same as shifted by U. Sometimes the geometric say that if you shift by parameter U, then you create a Poissonian field with this. Now, let me give you a comment on the literature on this. First of all, this looks pretty much like a generalization of the second Raynight theorem. What is the Raynight theorem? Now in dimension 1, we look at Brownian motion in dimension 1. We look at its local time. This is the time t at location x. And you wait until the local time from 0 is larger than u. This is the sigma u. Then if you replace x by t, here you have that the law of this guy here with the parameter u, this is how much local time you had, plus b squared is the same law as the Brownian motion shifted by square root of u. This is called the second Raynight theorem, which was done already in the 50s. Now, we're not, of course, the first one to look at this type of, so this was in one dimension. So it has nothing to do with, in some sense, the Raynaud theorem is just one-dimensional special diffusion local time property. Now, we're not the first one, okay, who realized that there's a relation between this type of result and the gradient field. And the first one was done by Duncan in '83 already. But let's say, to put it into the interlacement picture, this was done by Snitsman in another math a while ago. And also, Eisenborn, Kaspi, Marco Rosen, and Xi looked at this type of isomorphism. There are some further results by Lejean and Lupu and all of this. I cannot tell you all of the reference because this is a lot of people who worked on that. But let's look at the application. So the main application were used by my co-author, Rodriguez, and other in the percolation. So in some sense, we can use this identity here to understand the percolation structure of the level set of the Gaussian free field plus the square root of 2. And also Bauer, Schmidt, and all also looked at relation between four random walk. Ding and Perez discovered time. There's a whole bunch of very interesting results based on this type of equality. Now, let me go back to the results that are presented. And basically, it's in some sense, it's a kind of a Laplace transform, and we can use it for a lot of applications. But the trouble is, we don't have equality in law. And it turned out the reason why we don't have equality in law is because the random walk the law of the random walk is affected, the environment is affected by V. But this disappears in the scaling limit. And this is one of the motivations why we're now dealing with the next result, which is scaling limit. Now, this only works in dimension V larger than equals 3, which is, I explained this in a while. So we rescale the field in this way. There's a very beautiful result of Naddaf and Spencer, and also done in a dynamical way by Jacobin, Ola, and Spohn, which says the following way, that if you rescale, this is a static result, the result is dynamic. If you rescale this field appropriately, then this will converge to there's a matrix of the homogenization result in some sense. There's a strictly positive definite matrix, so that this field here converges as a distribution to the continuous Gaussian free field, where this is just, let me call it G of sigma. It's just a green function of the random walk with the matrix sigma. What we are now going to present is an extension in some sense. So we would like to deal not only with the free field itself, but the square. So in order to deal with it, of course, the square does not exist. That's why there's a device called Wick-product, where you just subtract the mean. So the standard way of dealing with it, you start with the modifier, where everything is very nice. You subtract the mean, and then you pass to the limit, which exists in L2. So we can define the Wick-product in dimension 3. I'll come to that why exactly dimension 3 is allowed in this business. And then our second main result tells you the scaling limit, that if you look at both the Wick-product square and this, they converge together to the law in the continuous case. In some sense, this here was done already by Naddaf and Spencer, and then we can also deal with it with the square. Not only that, we have a very nice expression, which maybe, and I would be very pleased if someone can give me some reference, which gives you what is the Laplace asymptotic of this, the Laplace transform. The Laplace transform converges to this expression here. So this expression here is clear because it's just the variance in some sense, but there's nothing new. But the other one is quite interesting. It just takes you a functional where in some sense what you have to do, you have to replace the green function by the green function square, properly rescaled. And you realize now why dimension 3 matters, because if you look at this, you take the square, and you know that the green function behaves like C, D minus D prime, the norm. Square is precisely in L2 log. So it will just be integrable, which is not the case in dimension 4, which would be critical. The motivation to deal with this is now we can now use this. We go back to the isomorphism. So in some sense, we're going to rescale the isomorphism to get a convergence and properly rescale. This is precisely the next result. So we're not the first one, of course, to deal with this. So both Lejean and Snitman look in the Gaussian situation. They have introduced the Poissonian interlacement model, which is very much similar to what I told you before, but of course you replace the capacity by the capacity of the Brownian motion, and you have the trajectory this way. It's just a Poissonian field with the following intensity, which is precisely corresponding to what I described before. You see the bin function of the continuum model. And then our corollary tells you that if you look at the rescale occupation time, properly rescaled, and this is measured, this will converge to the Poissonian interlacement model. And in fact, it turns out that the proof is quite simple because you just look at what would be the Laplace transform of this business here. And you just use the isometry to see that just a ratio between the two. So the shift is G and the shift between the two. You just plug in and this is what you get an equality from there. And from there on, you just pass to the limit because we know we have the limit, and then eventually we get this expression here. There's a little manipulation to see why we get this. I'll explain maybe a little bit more why this kind of Laplace transform come into the game. I want to stress one of the challenges in this business here. Of course, on the left-hand side, it's non-negative, but here this can be positive and non-negative. This is why you have to be very careful by allowing a function b which cannot be both positive and negative. Another corollary, which is maybe the asymptotic of the isometry, which tells you that if you look at the properly rescaled field that we have here, this and the Wick product, therefore they converge to the corresponding one. Now, since I have a little bit of time, let me give you some ideas on the proof. I want to really, and this may be one of the important points in the whole talk. There are, of course, proofs. And if you look at the proof of Schnitzman and Kashpi and others and Duncan, they all rely extremely on the Gaussian nature of the problem. So our challenge was, can we cook up a proof which does not depend on the Gaussian nature, which is just very general. And it turned out that the magical tool is just a Feynman cap. So let me just recall you what is the Laplace transform of a Poisson point process. So this is the intensity. So the Laplace transform, if you log of the Laplace transform, is just the intensity acting on this function here. And now we just apply this interlacement, and this is where you come here with the equilibrium charge. So we take a function v which is supporting k. So this is basically what you pick up here. And this is just the definition of this measure. That's why you have this strange double integral, which I explained very soon. And I use the fact that the equilibrium charge can satisfy this equality here, and just by integration by part, basically you get first this expression. Okay, so this is just preparation. So you basically look at the Laplace transform of the Poissonian, and then you ask yourself, what is it good for? Well, you realize that the isomorphism theorem is just the same as proving the following fact. You look at the Laplace transform of this is this times this, because just the square cancels out. So it's easy to see. So basically, this is what we have to be shown. So on the left-hand side is the Poissonian business, and on the right-hand side you have the shift. And now, of course, the point is how to compute this guy here. And this is very standard way of computing this. So basically what you do, you define f of tau, we just put the parameter tau, you take first derivative and second derivative. So basically you can express this guy here as a double integral. That's why you have a double integral of variance, which is quite standard. And now the point is, the variance by the random walk representation is just the green function here. So you just plug it into the game, and this is why you get a nice expression for that. What about the scaling limit? The proof of the scaling limit? Well, it's standard also. So what you do, you just first use the modifier to define it as a function. And basically, it's easy to see that because if you use a modifier by the Naddaf and Spencer result, because it's a continuous, and that you have the convergence for the modified field to the modified Wick product. The trouble is, of course, and it's easy to see that this will converge to that. The trouble is, of course, to interchange the limit with n infinity and epsilon, and this is based on so-called exponential tightness. So the exponential tightness will just tells you that for v small enough, you can actually prove that the lim sup of this is properly rescaled of the exponential. The next point is to relate the modified field with the other one, also interchange the limit, and then basically we just put at the variance between the difference of the two. Now, how do you get exponential tightness? How do you get this type of estimate? And the point is about the same strategy. You define f of tau, you put the parameter tau here, you differentiate first and twice, and eventually what you end up having is just a variance of phi squared. You see, this is pretty much like what I did just before, but the difference is, of course, that it's a square now. You see, this is what we have here. Now we have a square. So basically, you have to deal with the square in order to make sure that everything is fine. And this is absolutely non-trivial how to deal with the square. And this is what we use. We use an extended form of Braskamil. In such an you iterate Braskamil inequality, where you use, of course, this is the part, remember the parameter I said that the second derivative was larger than C1, uniform elliptic. And then basically what you pick up here is this guy here to the square. Now, I would like to make sure that you understand it's, there's a mixture, of course, of interlacement business and these kind of things, and of course, of potential theory. But there's also a mixture of local limit theorem. And this is basically why it works. It's not just the standard homogenization, it's local limit theorem. And you see why? Because here, basically, you take the square. It's a local limit theorem. Local limit theorem. We just finished with the given outlook. So far, it's not clear why would you use form. I mean, of course, what you would like to do is now interlacement for the Landau-Ginzburg model. That would be interesting also to understand the uses to get some information about the percolation. Now, what is outlook? Well, first of all, what about dimension 2? Of course, in dimension 2, it's recurrent, so you have to pin it. So you pin at 0. The scaling is slightly different here. There's no parameter in front. And in dimension 2, of course, because the singularity is logarithmic, you can use every Wick-orderedsquare power, and you can even, if small enough, you can be dealing with the scaling limit for the exponential when alpha is smaller. One of the applications, we have another paper in preparation to use this isometry is isomorphism, is just to show how to create a mass. So you see, these models were mass-free, so it means that the reference measure was just a product measure. That's why you have a continuous symmetry. So we want to somehow to change the continuous symmetry with some parameter rho, with a function rho, which is not flat, and we can use this business to get to prove that we have a mass. What it means, mass, that as soon as if you change appropriately the reference measure, you got the symmetry, that you had an exponentiality of the correlation, which has been done in other settings, but we can do it in a very robust way. And finally, let me just remind you that everything which was done on ZD doesn't matter. You could put any graph, for instance, a calculation graph to also get the result. Okay, so thank you for your attention.
Thank you, Jean. Thank you, Jean-Dominique. A nice and intense lecture. Is there questions?
I have one question.
Question online.
Oh, hi.
Roland.
Hello. Yeah, my question is, in the Gaussian case, having the square is very useful if you want to add, say, a quartic interaction. So if I understand correctly, what you could imagine doing is having a gradient model plus a quartic interaction. Is that correct? Is that the kind of measure that you can get using your new isomorphism theorem?
Yes, sure. And at this point, we haven't go into this. We were more interested in putting to look using Szymanski representation just to get the math. But of course, this is very appealing to perturb it to a quartic field with non-harmonic situation.
Okay, yeah. So I guess this in the Gaussian case, this representation is extremely useful to learn all sorts of things about this phi-4 model. And it'd be very interesting if you could do the same with an anharmonic gradient part.
Okay, I will ask our co-author, Pierre-François. We have a joint co-author, and then that definitely would be an interesting thing. But we haven't tried it yet.
All right. Yeah. Well, thank you very much. It's very nice.
So my question, so thanks for the talk, first of all. So if you consider some random conductances, so you plug in some random couplings in your Hamiltonian interface for the quadratic interaction, is this case covered by your analysis? Can you extend?
So maybe just go back to, of course, you can do a deal with this. What is very relevant, and I forgot, yes, what is really relevant is this business here. Of course, let me just put it this way. This could depend on X and Y, and the important is it's strictly convex, because if you have a random walk representation, you can deal with this. So of course, you could alter this to put the long range or short range, whatever. So for the isomorphism, it's very general. Does this answer your question? So you could put, for instance, the special case, you just put alpha of xy times grad phi of xy square. But this could be random. Or another point, which is also we might be dealing with, is the following: replace GD, okay, by a Poissonian field. See, the basis will be a Poissonian field, all right? So you will have an interface. So you put just a point at random, then you put gradient interaction with the nearest neighbor, for instance, and then try to get this. And as long as you have homogenization for that, you could possibly also get the result.
Okay, thanks.
If there are no other questions, we are a bit short in time. Thank you very much, Jean-Dominique. Hope to see you soon in presence.
Thank you very much.
Have a good day.